I'm Grace Jansen. I'm a developer advocate at IBM in the UK, and I sort of primarily focus on Java and reactive technologies within sort of the JVM ecosystem. So today I'm going to hopefully be taking you through sort of reacting to this event-driven world that we now find ourselves in. So how do we create applications that are suited and make best use of tools and technologies so that we can really be as reactive and responsive to the events that we're generating to provide that really responsive experience to our end users. So let's get started. So I know it's early for you, even earlier for me here in the UK, so it's definitely time to grab some coffee, and no talk seems to be complete without a coffee demo. So we're going to be utilizing a coffee demo to take a look at why any of this is really needed in the first place. So let's take a look at a coffee example. So in this case, we have coffee lovers coming in and they want to order some coffee in a coffee shop. So they send that HTTP to the coffee shop, and that HTTP request then goes to a barista for them to make the coffee. Now there are plenty of examples out there that are sort of along similar lines to this. This example particularly was made by our cousins over at Red Hat, and you can access this demo application. It's all open source using the link at the top of the slide here. Now, the difficulty with this is that the coffee lovers, when they order their coffee, they essentially have to wait for each individual coffee to be processed by that barista before the barista is freed up to make the next person's coffee. So it's wasting sort of the coffee lover's time. It's not making best use of the barista's time because there's sort of time in between when the barista's perhaps waiting for a machine to make the coffee, where the barista's time is also wasted. So it's not particularly responsive. It's not particularly reactive. In order to make this a bit more sort of reactive and to make it a bit more sort of asynchronous instead of being so blocking in this case, it's often the case that people will recommend using event-driven architecture. So event-driven architecture, it's sometimes shortened to EDA, is a popular architectural approach that really enables events to be placed at the very heart of the system. So it's really about having events as records of something that's happened, and it's essentially having this sort of this log of state immutable events that are happening, and they're ordered in sequence of their creation. So it's essentially, you can see here we've got an example. You can see the event messaging backbone here in the middle, and we've got microservices that are either publishing events to that backbone or consuming events, or perhaps doing both. So you can see here servers 3 and 4 are doing both. If you want to see some of the advantages of event-driven architecture, we've written up a blog here that you can access with the link at the bottom of this slide here. So you can check that out at a later date, really to understand the benefits and advantages to switching to this. So what this looks like when we're going back to our application is we're still using HTTP to send to the coffee shop to access, sort of to place our order. And then once the coffee shop receives that, it puts that order onto the event backbone as an event. That means that those events are stored up in this queue or in this topic in Kafka, for example, and then the barista is able to read from that backbone when they're sort of free to do so, and then they update a board to let the coffee lovers know when their coffee's been made. What this means is that the coffee lovers don't have to wait at the kiosk in the coffee shop until their order is complete. They can go away, chat with their friends, probably discuss Java at a table somewhere, and they can essentially make better use of their time because they're no longer blocked waiting for that coffee order to complete. They can essentially just monitor the board, check when the board is updated with their coffee order, and then they can go and collect it. So it means it's a lot less blocking, it's a lot more asynchronous in this manner. And a useful tool for implementing this kind of architecture, which I've already mentioned, is Apache Katka. So if you've not come across Apache Kafka before, it's an open source and a distributed streaming platform that enables sort of this stream history. It has immutable data, and it's really highly available, which is fantastic when we're trying to build reactive responsive systems. But what this often leads to is once they implement this sort of event-driven backbone, as you can see on the right-hand side here, they come to this question. So now that you've implemented event-driven architecture, is your coffee shop now non-blocking and highly responsive? In other words, is your microservice system non-blocking and highly responsive? And the answer people often assume is, oh yes, of course, I'm using Kafka. That's not the whole story. Event-driven architecture is a fantastic architectural style that enables less blocking within your application and greater decoupling, for example. But just implementing a tool like Kafka does not magically make your system non-blocking and highly responsive end-to-end. That's where something called reactive systems comes into play. So reactive systems is essentially all about, it was based on this manifesto that was created back in 2014. And this manifesto lays out the key characteristics and behaviors that we want to be experiencing within our application in order for them to be reactive and responsive and asynchronous from end to end. So it's made up of 4 characteristics. The first of those is message driven. Now, interestingly enough, in the original manifesto, which was built in 2013, they actually included event-driven, but they switched to message-driven in the Reactive Manifesto 2.0 in 2014. And there's a whole blog you can read on that, which is online if you want to know the specifics about why they made that change. But what's the difference? Because often we associate Kafka and event-driven architecture with events. So what is the difference between message-driven systems and event-driven systems? We've got a definition here for messages and a definition here for events. So we've defined messages as an item of data sent to a specific location, whereas we've defined events as a signal emitted by a component upon reaching a given state. But actually, when you compare them, interestingly enough, you can kind of have a hybrid of the two. So you can actually have a message that contains an encoded event in its payload. But when it comes to Kafka, none of that really matters. If you take a look at the Kafka website, it actually never mentions messages or events. Instead, it references records. So it says, how Kafka enables you to publish and subscribe to streams of records, store records in a durable way, and process streams of records as they occur. So actually, Kafka has deliberately moved away from these sort of charged terms of events and messages because it can be used for both. It can be used for message-driven systems and event-driven systems. And it's that message-driven system within Reactive that we want so that we can really enable a decoupling of the services and the components of our application so that failure in one, for example, doesn't affect another. And we can make it as asynchronous and non-blocking as possible. So although Kafka does help us to sort of, and that event-driven architecture style does help us to implement one characteristic of the Reactive Manifesto, which is that message-driven backbone, let's take a look at our application and what problems might occur if we don't implement the other characteristics, which would be the case in the original application where we just put in Kafka. So here's our original application, and this is working fine for just now. But there aren't just 3 coffee lovers in the world. What happens in the case where we have many, many, many more coffee lovers coming into our coffee shop, all trying to place orders at the same time? Suddenly, our coffee shop has a lot more orders to deal with. And although these can be placed onto the event backbone, and it does enable, because we've got this event backbone in place, we've got this Kafka infrastructure in place, and we're putting our orders onto this event log, our coffee lovers are still able to go off and have their fantastic discussions around Java. So they're still non-blocked. But we still have blocking in our system because we still have all of these coffee orders to get through, and we've only got one barista to do that. Our barista can only work so fast and only work on so many coffee orders all at one time. So we've actually got a point of contention here. We've got a point of potential failure because we are putting huge amounts of stress and load onto this single barista service to be able to deal with all of these requests. And this is where the behavior of elasticity comes into play. So elasticity is actually, in the original manifesto, they had scalability, but they've switched to elasticity because it's not just about scaling up, it's also about scaling down. So elasticity, this elastic behavior, is all about being able to both scale up and down depending on the load placed on your system. So if your load increases, say you've got an influx of coffee orders, you should be able to elastically scale the resources within your application to deal with that. But then when those coffee orders or coffee lovers leave the coffee shop and you've not got anyone ordering, you want to be able to scale those resources back down to be as cost effective as possible. So let's take a look at what this means for our application. Well, by utilizing this elastic behavior within our application, we'd be able to scale up the number of barista services as that load increases. So by scaling up the number of baristas, we're enabling more of those coffee orders to be processed in conjunction, at the same time, basically, which means that we're providing a much more responsive, a much more reactive, I guess you could say, system. So our coffee lovers will get their coffee orders much, much quicker and be much happier. So it's an important behavior to consider. Let's get back to our barista example. Now let's assume we've got an extra component in this example. So this extra component we're going to call the serving table. And in our example here, the barista, in order to serve up the coffee and say that it's ready to complete, must place the coffee orders onto the serving table. Now, this serving table can essentially represent either a downstream microservice that's needed for extra processing, or perhaps an external service like a database, for example, that you rely on. So in this example, the barista has to place the coffee orders down in order to proceed. What happens if the barista has lots of coffee orders and essentially the coffee table, let's say our coffee lovers are being a little bit lazy, they're taking a while to go and get their coffee from the coffee serving table. So the coffee serving table is now full and our barista is juggling coffee because he can't put it down onto the table. So at this point, this is essentially representing that external service or that downstream microservice going down or becoming unavailable temporarily perhaps. And our barista service now can't continue because it's essentially stuck with coffee orders waiting for that service to come back up. This is a potential point of failure for application and could cause our application to potentially become essentially not able to be used. So you've essentially failed with your application here. So this is where the behavior of resiliency is really important. We need to be building in inbuilt resiliency into our application. So in the potential case of any failure within our system, any failure in our own code or in any perhaps backing services or external services that we rely on, that we are able to continue our application as best as possible and that we're able to put in place behaviors to try and get that back up. So in the case of the previous example with the barista, we could perhaps put in place something like back pressure. So essentially back pressure would enable the barista to feed back to the event backbone to perhaps say, could you rate limit the number of requests coming to me right now because I'm stuck waiting for this downstream component to come back online again, to potentially prevent that from becoming a point of contention. We could also introduce things like circuit breakers to potentially break the circuit to that particular barista, instantiate a new barista service and a new coffee serving table so that we continue on with those requests. So by placing in resilient behaviors, we should be able to gracefully deal with these potential failure points and enable our application to remain responsive, regardless of any failures we might be facing. So we've looked at message-driven, we've looked at elasticity, and we've taken a look at resiliency. And these all together combine to enable this last characteristic of the Reactive Manifesto, which is responsiveness. So being able to respond as quickly and as effectively as possible to event changes and state changes within our application. So by implementing all of these characteristics, we should be able to create a truly reactive and responsive application. But everything I've mentioned so far has been sort of fairly high level, basically based on general behaviors we should be seeing. How do we actually go about building reactive systems and enabling those reactive characteristics within our own applications? So I've got a fairly basic application here just to demo the various different levels we need to be thinking about when it comes to reactive. Now, we had a look at Kafka and how enabling that sort of message-driven infrastructure enables us to decouple the aspects of our application and gives us some of those behaviors. But that's at the data level. That does not help us make our applications reactive end to end. So there's various different levels. The data level is one, and Kafka does help with that. What are the other various different sort of levels we need to be looking at within our application to enable this behavior? So the first level is sort of, if we look at it from sort of a wider view, is how do our different components, or our different microservices in this case, communicate with each other? And we can enable this behavior, this communication between microservices to be reactive by utilizing something called reactive architecture patterns. So here's some examples of reactive architecture design patterns that you could utilize. These are just examples. There are many, many more out there. If you Google reactive architecture design patterns, you'll see many listed in addition to these. But these are some of the more sort of common or more frequently used that we've come across within reactive applications. So the first of those is CQRS. So CQRS stands for Command Query Responsibility Segregation. It's essentially, when you break it down, all about splitting up that read and write APIs to enable higher availability of the data within your application. Then we've got circuit breaking. So if you've done electrical engineering, for example, you've probably come across this term before. So circuit breaking in software is fairly similar. So in circuit breaking, what happens is an upstream component recognizes that a downstream component is perhaps under stress or load, or is potentially stuck in a process of some kind. And it can do that by essentially analyzing its logs. It might be potentially seeing the same failure message again and again and again. And what that upstream component can do is temporarily stop requests going to that downstream component and instead reroute them to an alternative downstream component. So it might be a duplicate microservice in that case. And what this means is by breaking this circuit, by stopping the requests going to that downstream component, it means it gives that downstream component time to get better again, time to recover, to come back up, to finish whatever process it might be stuck in. And once it's healthy once again, that upstream component can then reinstantiate that route down to that downstream component and start sending requests to it once again. So it stops it becoming a potential point of failure, a potential point of contention, and enables it to gracefully deal with that potential stress or load or failure that it's sort of dealing with. Then we've got sagas. So sagas are essentially a mechanism to take more traditional transactions that we might have done in, say, a monolithic architecture and do it in a distributed manner. So we create what we call sort of multiple microtransactions that have this fallback behavior to account for things going wrong potentially partway through. So it's a sequence of local transactions where each transaction updates data within a single service. So really useful if you're relying on perhaps other processes going on in other components of your application. And then back pressure. So I've already mentioned back pressure before as a potential solution in that Barista example we were looking at to increase our resiliency. So back pressure is a feedback mechanism from a downstream component to an upstream component that enables us to help rate limit requests or messages coming to that downstream component to prevent it becoming a point of failure or contention and to enable it to sort of be able to deal with that load at that time. So back pressure is actually a really commonly used pattern in reactive architecture, and it will be used in some of the frameworks that we'll be taking a look at later in this presentation. So that's between the microservices, sort of at the highest level of your application, looking down. But what about within our microservices? So we also need to ensure that the code and the logic we're writing within our microservices is also reactive and asynchronous. And to do that, we can utilize reactive programming patterns. So what do I mean by reactive programming? So here's a very basic definition of reactive programming. So it's all about this asynchronous style of programming. So in this example, in reactive programming, in this paradigm, it enables the logic to be driven forward via the availability of new information rather than a thread of execution. So it really does focus on this asynchronicity. And you can utilize several different patterns to enable this. So as Java developers, you're probably familiar already with the term of futures. For those who aren't, it's essentially a promise to hold the result of some operation until that operation completes, very asynchronous. Then we have things like reactive programming libraries, and they're really designed for composing asynchronous and event-based programs, so enabling many of the characteristics we've seen in that manifesto. And examples include RxJava and Small Mutiny. And many of the frameworks we'll take a look at utilize these reactive programming libraries within them. And then we have reactive streams. So reactive streams is a community-driven specification that was really designed to provide a standard for handling these asynchronous data streams in a non-blocking manner while providing that all-important back pressure that I mentioned. So these are some of the patterns you can utilize within your microservices, within the logic in your application. So we've looked at sort of the data level, looked at how Kafka can be really useful for that. We've looked at the wider architectural level and how reactive architecture patterns can be useful for that. And we've looked within our microservices, within the logic in our application, to look at how we can enable reactive through programming patterns like these. So how can we make sure that we're utilizing Kafka within our applications to really ensure we're getting those reactive behaviors as effectively as possible? So we mentioned that Kafka is a fantastic tool for enabling this message-driven asynchronous data layer. So we're going to move on from that because I think that's been discussed in enough detail already. But how do we enable these other characteristics through things like configuration within Kafka and through sort of ensuring that your application is designed in a way with Kafka to enable them? So the first one we're going to take a look at is resiliency. So it's really important that we build in these resiliencies, and actually there's many different features in Kafka that enable that resiliency sort of built in. So the fact that Kafka has this ability to essentially retain messages, so it's different from traditional queuing systems in that it provides this stream history. So when a consumer reads a record from Kafka, that record isn't removed from the topic. So both the consumer and any other consumers could reconsume that record at a later time. So this stream history is really useful for enabling consuming applications to recover from a potential failure. The stream history within Kafka allows applications to use the inbuilt Kafka features to recover from failures that occur potentially mid-processing, rather than requiring the application to use an additional persistent store to recover from that failure. So that immutable data and stream history can be really useful in enabling our application to be resilient. Kafka also has built-in resiliency within it in the way that it works. So when you start up a Kafka cluster, it consists of a set of brokers. A cluster usually has a minimum of 3 brokers, and we'll see why in a minute. We'll see why that's important. Now, Kafka is then broken down further into topics, and these topics are where we store our records. So a topic is essentially a sort of logical grouping of similar kinds of messages or records, and you define which messages and which records go into which topic. So you make that distinction. So for example, you might have a topic for coffee orders, and you might have another topic for user information updates. Within a topic, you'll have one or more partitions, and these partitions are distributed across the different Kafka brokers. So you can see here we've got partition 1 for topic A on broker 1, partition 2 on broker 2, and partition 3 on broker 3. And we'll see where these partitions come in when we look at elasticity in a minute. But for resiliency, the key thing is that Kafka uses something called leaders and followers. So a leader for each topic, one broker is elected as the leader and the other brokers are followers for that topic. What this means is that essentially your application will update the leader and the leader will update the followers within the Kafka cluster. So replication is essentially done by the followers repeatedly fetching messages from the leader. This is all done automatically by Kafka. So in this example, we've got 3 replicas. So we've got 1 leader and 2 followers. So all our apps will connect to the leader, they'll consume from and produce to the leader. But what happens if the leader goes down? Well, that's fine because we've still got 2 copies of the data in the followers, which is where that extra resiliency comes in, because we're not losing our data if that single broker goes down. In fact, if that broker were to go down, we essentially lose our leader. But Kafka has this fantastic ability to create a leader election, it's called. So essentially, the followers then essentially get, one of them will be randomly assigned as the leader. So that means that this new leader is elected, it's healthy, and all apps are able to automatically transfer across to connect to this new leader broker. So even if you have a broker that goes down, Kafka's resiliency in terms of having this multiple partitions, multiple brokers, and this leader election enables Kafka to have this built-in resiliency so you don't lose your data. So this is all fantastic and really great that Kafka has this built in, but how do we make sure that records from our application are successfully being sent and consumed from Kafka? How do we make resilient producers and consumers within our application logic when we're connecting to Kafka? So in terms of resilient producers, as the name suggests, a producer is essentially the name of an application or a microservice that's sending records or messages to Kafka. So it's producing to Kafka. There's a couple of things you need to consider when it comes to producers and their config. One of those is it's essentially about your delivery guarantee and your configuration. So with reactive applications, it's not good enough essentially to just do fire and forget if you really want full resiliency, because if the broker goes down, your messages will get lost if you do your fire and forget method. So instead, we need to be looking at the two different delivery guarantees that Kafka offers, which is at most once and at least once. With at most once, you may lose some messages. It's not completely resilient, but if you don't mind if some of the messages don't make it, it essentially enables your system to be a lot faster, because obviously you're not waiting for each of the followers to make sure they've all got the message as well. You're only waiting for the leader to confirm it's received that message or that record. At least once, it means that you've got guaranteed delivery of that record to Kafka, but you may get duplicates. So just bear that in mind. But by utilizing at most once or at least once is at least more resilient behaviors within your applications than fire and forget. You've also got to think about your configuration. And there's two configuration values you need to be thinking about when it comes to your producer microservices. One of those is ACKS. That's short for acknowledgement. So this is essentially acknowledging that the record or message has been received. And you can either configure that to 0. So 0 is when you really don't care about getting the message acknowledged. It's very good for fast throughput, but not good for resiliency, because obviously you essentially don't know if it's been received or not. 1, if you set ACKS to 1, it makes sure that the leader successfully received the message, or you can set it to all. So all means that you're essentially waiting for all of the replicas, so the leader and the followers, to confirm they successfully received the message or the record. So that acknowledgement strategy is really important to enable that increased resiliency within your application. And then we've got retries. So if your acknowledgement times out or fails, essentially this configuration value determines how many times you want to retry trying to send that message. So how many times do you retry producing the event, and how will that retry potentially affect ordering? So there is the potential for it to affect ordering within the records within your topic in Kafka. So do bear that in mind if you are doing multiple retries in that configuration. So Kafka does offer sort of resiliency through these configuration values for your producers. But what about consumers? So with consumers, when you're consuming from Kafka, you want to make sure that all the messages have definitely been read. So for this, you need to think about something called offsets, which is another configuration value. So unlike other messaging systems in Kafka, once the message or the record has been read, it's in traditional messaging systems, it's no longer in the queue, but this is not the case for Kafka. It remains there. As we've just discussed, we have that stream history. But this means that you need to keep track of where the consumers have gotten to when reading across that topic or across that stream. And this is where offsets come in. So offset is essentially the value assigned to each record within a particular topic, and it essentially just goes up in numerical value. So when a consumer is reading from a topic, they essentially have something called, they commit an offset. So they commit that number when they've read or processed that particular record or message from the topic. And we need to store our offsets so that if, for example, our consumer goes down, when it comes back up again, it can access that stored offset, find out where it was. Perhaps it was at number 1, so it knows not to start at number 1, it knows to start at number 2 in this case. So there are 2 different ways of committing offset. There's auto commit and there's manual commit. So we'll take a look at our Barista example again to see how these differ and how how these basically enable greater resiliency through these different types of committing. So let's take a look at auto commit first. So auto commit is essentially where you have no code in your application to specify when you're going to be committing that offset. So it's essentially relying on default settings in the underlying client, which is usually a Java client. We are at a Java conference, and it's based on a timer. So essentially your offset will be automatically committed on this timer basis once they've started reading the message from Kafka. Now, what does this really mean? So if we have our Barista here, our Barista is reading from our topic. So we've got 3 records in our topic, 3 orders essentially. So we've got a coffee order, a cappuccino order, and a latte order. So our barista starts with its coffee order, and because we're using this auto commit based on the timer basis, that offset is committed to say, yep, we've read and we're processing the coffee order. So then, unfortunately, our barista has a bit of an accident. And whilst making that coffee order, he spills it and drops it, and we no longer have that coffee order. This is essentially the same as that barista microservice perhaps going down, coming back up again, and now it needs to know where to start at in that topic. So it fetches its committed offset, which in this case, it thinks it's already, it has already committed the offset for coffee. So it thinks it's already made it. So instead, it's going to start at cappuccino. So our barista makes the cappuccino and makes the latte, but what this means is that we've actually missed a coffee order. So this is a slight issue when you're using auto commit, because you have that potential to lose a record because you perhaps go down mid-processing, and it's based on that timer. So instead, we can look at manual commit. So manual commit is when you add code into your application that specifies when you want that offset committed. So in this case, we're not going to commit our offset until we've completely finished processing our coffee order and it's served up to our clients, to our coffee lovers. So in this case, we're not committing that offset until we literally serve up that coffee, as you can see here. So now we've committed that offset. And then we go through and make cappuccino and latte. And this means that if our barista was to go down mid-processing, we wouldn't have committed that offset. So when our barista comes back up, it would know to start at that coffee order. So in that case, it's much more resilient to potential failures mid-processing. So this is how we can enable greater resiliency within our consumer microservices in our application. So we've taken a look at how Kafka has built in resiliency through its message retention, stream history, through its broker and partition systems, leader elections, and we've taken a look at the configuration we need within producers and consumers to enable greater resiliency. What about elasticity? So as I mentioned before, elasticity is all about being able to scale responsively depending on the load to your system. So Kafka is designed to work well at scale and to be scalable itself. So it does this in producing applications using partitions. So in a topic, there's usually one or more partitions. In this case, we've got 3. So actually, when I created the topic, I specified that I wanted 3 partitions. So it is something you need to specify when you're designing and first creating your application. Now, Kafka will aim to spread these partitions from a particular topic out across different brokers to enable that greater resiliency. But this also allows us to scale producers really easily, as we won't have to load for one particular topic on one broker. And we can add more brokers if we want to, and we can add brokers if we want to spread the load out more, essentially. But for Kafka, the thing we really need to think about is consumers, because consuming in the application is where this elasticity is really interesting, because scaling up the producers is fairly easy because we just scale up either the number of brokers or topics, etc. So in consumers, when we're consuming from Kafka, this elastic behavior is made possible through something called consumer groups. So when you're consuming messages from Kafka, you need to think about how you're going to handle this stream history. Essentially, because you've got this stream history, there is the potential for consumers to read the same message twice. So how do we enable that scaling up of consumers all reading from the same topic, but prevent that message or record duplication? And this is where these consumer groups allow for this. They allow scalability of consumers without this potential to duplicate records. So here we have 2 consumer groups. We've got consumer group A and consumer group B. We have our topic that we had before on our different partitions, so partition 0, 1, and 2, and we have some records in there already with their offsets in those boxes. So in this case, we can imagine each consumer is sort of a different Java application, and they've joined their consumer groups by providing a group ID to Kafka in their configuration. So that is something you need to provide in their configuration. So in this case, in consumer group A, because we've got 3 partitions and we've got 3 consumers, they're actually going to get 1 partition each. So Kafka makes sure that the consumers in the same consumer group read all of the messages from a topic by assigning a partition to each, because consumer group, that's the way Kafka ensures that there isn't duplication, is that it's based on partitions. So For consumer group B, because there's 2 consumers, but there's 3 partitions, one of them, so you can see here the second consumer, will actually be reading from 2 partitions. What this means is that between all of the consumers in that group, they'll have read all of the messages, but they won't have read any duplicate messages. From an ordering standpoint, Kafka provides this ordering guarantee per partition. So the first consumer will get messages from partition 0 in the correct order. So that's why we can't have multiple consumers reading from the same partition, because then that ordering guarantee is not guaranteed. So that's why we have 1 partition per consumer. Now, if we were to add, for example, let's say we have extra load going on our system, so we want to add an extra consumer. Now, if we were to add an extra consumer to consumer group B, that would be completely fine, because we'd just take one of the partitions that was going to the second consumer and assign it to the new consumer. Totally fine. That enables us to scale up. However, we need to be considerate when we're setting up our applications of how many partitions we're creating and how many consumers we may need in the future. Because if we were to try and add a consumer to consumer group A, it would actually be defunct. It wouldn't read anything because there aren't any additional partitions for it to read from. And we can't assign the same partition as another consumer because we lose that ordering guarantee and we risk reading the same record and processing the same record twice. So this consumer would actually just sit there idle. So when you're configuring consumers in Kafka, you do need to consider how many consumers you're likely to have in your consumer groups at any time, and whether you have enough partitions for all of those consumers to work together. You can add new partitions to your system whilst your system is running, but the more partitions you have, the more load you're putting on your system when a leader election happens. And another issue you need to think about is that ordering is only guaranteed while the number of partitions remains the same. So as soon as you start trying to add partitions, you do lose that ordering guarantee once again. So when you're setting up your application, it's really important that you think about and you really consider carefully how many partitions you're setting up versus how many consumers you might potentially need within a consumer group reading from that topic. So this is how we can enable elasticity within producers and elasticity within consumers to be able to really enable those reactive characteristics in order for us to be responsive to these event changes within our system. So how do we actually go about writing reactive Kafka applications? So let's take a look at some tools, frameworks, and toolkits that we can utilize to actually achieve this. So here's the sort of standard reactive Java Kafka consumer and producer classes. Now, although these do enable sort of some reactiveness in terms of being able to pause and resume, they're not really designed to be built to build reactive Java Kafka applications. So instead, what you should consider using is a reactive framework or toolkit, as these provide sort of simplified Kafka APIs that are reactive. They provide that built-in back pressure that we've been looking at all throughout this presentation is really important. And they enable asynchronous per record processing, which is really important so we don't get that blocking processing for these records. So here are some sort of reactive frameworks that you could utilize. This is not an exhaustive list. There are alternatives out there. For example, Spring Webflux. I'm just taking a look today at these 3 different frameworks. So we're going to be taking a look at the Alpakka Kafka connector. So the Alpakka framework, which is a library which utilizes the Akka framework. And then we're going to be taking a look at MicroProfile Reactive Messaging, which is a specification as part of the MicroProfile stack. And then we're going to be taking a look at the Vert.x Kafka client, which is part of the Vert.x toolkit. So Alpakka is, as I said, a library which utilizes, which essentially works with Akka, which is another reactive library. And this is based on a slightly different system. So this doesn't utilize microservices. Instead, this is built upon the actor model. So the actor model, if you've not come across it before, is a conceptual model that helps deal with concurrent computation, where in this case, it's the actor that's the primitive unit of computation. So it's the thing that receives a message and does some kind of computation based on it. These messages in the actor framework are sent asynchronously to an actor that stores them in their individual mailboxes until they're able to sort of get to them and process them. So the Alpakka framework essentially enables consuming and producing from Kafka with something called Akka streams, which leverages the reactive interface of the streaming library, its back pressure and resource safety. This does help to hide a lot of the complexity, especially when your streaming logic is non-trivial, like substreaming, for example, per petition, and handling commits in custom ways. So this is really helpful. If you're already utilizing something like the Akka framework, then the Alpakka Kafka connector might be a really interesting library for you to take a look at. Now, there's another library, or another, I guess I should call it an API, a specification called Eclipse MicroProfile. Now, Eclipse MicroProfile is really an open source, community-driven specification for enterprise Java microservices. So it works with Java and Jakarta EE, and it is built literally by the community. So it's built by individuals and organizations and vendors who are interested in enterprise Java. So there's lots of different committers from all over the world contributing to this. There's a set of APIs that it enables. So you can see here, this bottom triangle here is the default APIs that it enables as part of that standard stack. There's a new stack that's just been GA'd, I think it was this month or last month, which is 4.0, which has slightly more up-to-date versions of what you can see in this diagram. The MicroProfile community also develops standalone projects. So these aren't part of the standard stack. So the standard stack are the bottom triangle here, and they're mostly APIs to enable enterprise Java applications to build more distributed, sort of microservice-driven applications where, because they're distributed, they need things like health checks, metrics, external configuration, CDI injection dependency, things like that. So that's why the specification was developed in the first place. These standalone projects aren't yet part of that standard stack. The hope is that in the future they will be. But within that, we have something called reactive messaging, which is sort of the reactive answer to introducing reactive asynchronicity into your application. Now, the reactive messaging specification, or API, interoperates and makes use of two other specifications. So that includes the reactive streams operator, which is another standalone project within MicroProfile, and the reactive stream specification that we mentioned earlier in the presentation when we were looking at reactive programming patterns. So reactive streams, as I mentioned, is that specification for enabling a standard, essentially, for doing asynchronous stream processing with back pressure. So it defines sort of 4 different interfaces to allow components to sort stream processing and to be connected together. And then MicroProfile Reactive Streams Operators, which is that other standalone project you can see, is a MicroProfile specification which sort of builds on top of the Reactive Stream specification to provide a basic set of operators to link different reactive components together and perform processing on the data which passes between them. So we're going to be taking a look at sort of reactive messaging, which utilizes those 2 specifications. So MicroProfile Reactive Messaging works by annotating an application's beans methods with either at incoming annotations or at outgoing annotations. They are connected together, so the at incoming and at outgoing annotations are connected together by something called channels. Now, a channel is literally just an opaque string. You can have either internal channels or external channels. An internal channel is essentially just between 2 methods within an application. An external channel is actually called a connector in this case, and that connects to external messaging brokers like Kafka, for example. Each implementation of MicroProfile has different channels and connectors. So, for example, OpenLiberty, which is an implementation of MicroProfile, has something called the Liberty Kafka connector, because it's a specific. Each implementation obviously specifies the type of connector. So in this case, Liberty, because we're utilizing OpenLiberty, and Kafka, because we're connecting to the Kafka message broker. So as you can see at the bottom here, you can see how method A and method B's at outgoing and at incoming annotations are connected together via that order channel. So you can name these channels whatever you want, they're just opaque strings. So this is how MicroProfile Reactive Messaging enables that more asynchronous, more reactive form of communication within your application. The last one we're going to take a look at, the last framework, is Eclipse Vert.x. Now, MicroProfile is specific to Java, but Eclipse Vert.x is actually a polyglot toolkit. So it can be used with Java, JavaScript, Scala, Kotlin, and many other languages. It's based on something called the reactor pattern. So the reactor pattern is an implementation technique of sort of more event-driven architecture. So it really builds upon that concept we mentioned earlier. So basically it uses sort of a single threaded event loop, blocking on resource emitting events, and then dispatches them to corresponding handlers and callbacks. It runs on the JVM. It is, as I just said, non-blocking and event-driven. It includes this distributed event bus, and it is single-threaded, which was actually really useful when we were doing our own demo application. So we had a demo app that we wanted to convert. It was just a basic Kafka app, so it looked a bit like this. We had a Vert.x. It wasn't Vert.x before. We had an application that essentially we wanted to build so that people who were making applications could test their Kafka aspects. So test that they had their security correctly implemented, that they were able to successfully produce and consume from Kafka. So our demo application was a very simple application. It produced a Kafka topic, and it literally consumed its own data from that Kafka topic back again. So very simple. You wouldn't necessarily do it in enterprise, but it was designed just to help you test your application. And we wanted to take that and make it more reactive, make it more asynchronous. We have a sort of front end for this so that we can see what's going on. We can input different data into our messages, into our records that are going onto our Kafka topic, and that's connected via a WebSocket. So we switched from a non-reactive to using Vert.x and creating a reactive application. And this is actually all open sourced, including the front end. So you can access this and utilize it. Please do if you'd like to test your own applications when using Kafka, and you can access that on GitHub using the link here. Now let's take a look at what our application actually did. So this is the front end for our application. We were able to put in sort of a custom message depending on what we wanted to put in, and we could select start producing. And that would send a WebSocket message to our application, and that would start producing to Kafka and then consuming back from Kafka when we selected start consuming. Now we also included buttons to be able to stop consuming and then restart consuming. And this is where it got a bit tricky. So you can see here how we have that start stop. So that meant that we needed to be able to pause and resume producing and consuming from Kafka. So in the original application, when using the standard producer client, the call to produce a record is a blocking call. So actually, let's take a look at how our producer changed when we switched to Vert.x. So when we switched to Vert.x, originally our producer was a blocking call, but now that we switched over to Vert.x, we're able to utilize a future to get back from the send function. So this means that our application is now able to asynchronously produce new records while waiting for the acknowledgement from Kafka of these in-flight records. This was a fairly small code change, but it did allow us to change from sort of blocking to non-blocking when talking to these external services like Kafka, which is a really important part of reactive systems. So this makes it easier to build the application to be more resilient when these external services are unavailable, like that Barista example when that coffee serving table went down. If the Kafka were to go down, we'd at least be able to acknowledge that and have that back from that future function so that we could essentially behave accordingly. So it wasn't a particularly massive change in terms of our producer, but we did see a significant change in our consumer. So in the original version of the application, we were having to use a for loop inside a while loop that resulted in this flow that you can see here on the slide when consuming records. So what happens is essentially we have to poll for records, and this poll function then returns with a batch of records. So you can see here we get this batch of records after 1,000, I think it's 1,000 milliseconds. And then once we've got this batch of records, we then have to iterate through each record in the batch. And for each record, we send the record along the WebSocket to the front end. And then we have to wait for this iteration to complete to return to step one. So essentially, whilst we're processing the current batch of records we have, no new records can be fetched. So they're just sort of building up, and then we have to wait and do another poll, grab another batch and come back. So it felt very blocking. It didn't feel very asynchronous. And another issue was that we had to sort of handle the life cycle of the poll ourselves. So the consumer is single threaded. So we had to handle these multiple threads ourselves of when we had to pause and resume again. So there was a lot of pain writing and debugging it. So when we switched to Vert.x for this consumer client, instead of having that poll loop, that for and while loop, we now have something called a handler. So we simply wrote a handler function that essentially is called every time a new record arrives. So this allowed much more asynchronous consuming and processing of records, which fit much better with the reactive paradigm. So in this flow, it was a lot simpler. Vert.x now is the one handling the step of polling for new records, so we don't have to worry about that. And we essentially now just receive a new record, send the record along the WebSocket to the front end using our handler. So this not only, it allows the application to process on a per record basis rather than that batching process, and it leaves the developer free to focus on the processing of the records rather than the work of consuming them from Kafka. So it really enabled us to utilize this more asynchronous style of programming. And we were able to utilize these pause and resume functions so that we were better able to sort of handle these different thread, the thread handling that we had massive pain with before, because Vert.x was now handling that for us in this handler. So it made it a lot simpler in terms of the logic for us to think through in our application. If you want to check out sort of all of our experiences and the lessons we learned when we were switching from a non-reactive Java Kafka application to a reactive Java Kafka application, we've written up this all into a blog here that you can access using the link below. So please do check that out. It goes into more detail of things that I've just discussed. So hopefully what I've shown you today is that you can't just take a non-reactive application, add a bit of Kafka in, a bit of Kafka jazz, and expect it to magically come out reactive. It doesn't work that way. You need to carefully consider the Kafka configurations that are best to enable the reactive behaviors that we want to see within your particular system. And you need to ensure that your application is reactive from end to end. You're enabling reactive asynchronous behavior within the logic in your microservices and between the various different components of your application. But you are not alone. We're not expecting you to build this from scratch. The open source reactive community is on hand to help, and there are many different open source tools like reactive toolkits and frameworks that can provide these additional benefits, like thread handling, like back pressure, and many others. If you'd like to get sort of hands-on with some of these reactive technologies, we've created a bunch of interactive labs that you can get hold of. They are free, and they're all based on this online environment, which means you don't have to have any prerequisites on your local machine. So in this, so you might want to check out the Creating Reactive Java Microservices, which is module 1. In this one, it's a reactive Java application, which connects to Kafka using that Liberty Kafka connector I mentioned. And these guides are actually utilizing the MicroProfile Reactive messaging specification. So different to the example app I showed you with Vert.x. So it might be interesting to contrast and compare them and to get hands-on with some of these reactive technologies and sort of integrating them with how you integrate them with Kafka. So definitely recommend checking out these interactive labs. If you'd like a summary of what I've described in this presentation, so essentially this free ebook that I authored helps just to have a reminder of sort of what reactive systems are, why they're useful, when to use them, and how to go about creating them. It's only a 30-page document and it is free online, so if you want to check that out, feel free. And as if I haven't given you enough extra reading, I have some additional resources here for you to check out if you'd like to go into more detail on sort of the basics of reactive. So we've got an intro to reactive series there and sort of getting started with reactive. I've also got these quick starters for Kafka. So if you've not used Kafka before, I would definitely recommend checking out the quick start guide here, which essentially gets you started using Kafka and Zookeeper in about 10 minutes. It's really quick and easy. If you're looking for essentially an operator for Kafka, you can check out Strimzy. And then all of the reactive Kafka libraries I mentioned, I have links here. So you can see we've got the Vert.x link, MicroProfile Reactive Messaging, Alpakka Kafka, and I mentioned there are others. So for example, there is Project Reactor, which is utilized in things like Spring Webflux. So you can check that out as well. And if you enjoy the interactive labs, we have more guides on our Open Liberty site, which implements that MicroProfile Reactive messaging specification I showed. So thank you very much for listening today. Hopefully this has been interesting for you and has shown you some interesting perspectives on sort of how to create reactive applications ready for an event-driven world. If you have any questions, I can answer them now, or you can contact me on Twitter using my Twitter handle, which is at the top of this slide here. Thanks very much.
Thank you so much, Grace. That was amazing talk. There are 2 questions to you.
Yep.
If you can switch to the Q&A section on your right side, you will see 2 questions.
How can we make sure that the event triggered by one system reaches all interested services? Fantastic. So an event, that's where Kafka comes in, right? So for example, I might have one producer, which is producing an event, but I might want several services to know about that event, right? And that's where consumer groups come in. So I might have several consumer applications that are all part of the consumer group, and they might be reading from the same topic, and they can all read the same topic. If I put them in a consumer group, it means you won't duplicate that information, but you don't have to put them into a consumer group. So for example, you saw that we had 3 partitions and 2 consumer groups. So for example, I could just put a single consumer in each consumer group, and that way they would all read every single in message or record from that Kafka topic. So that's why Kafka can be really useful, because it makes sure that every interested service or every interested party is able to access that information. Hopefully that answers your question. Let me know if it doesn't. Another question was, what would you use for logging your events in event-driven world, like having some event ID or transaction ID, which would be used for tracing afterwards? Thanks in advance. So logging your events in an event-driven world. So Kafka enables an event log itself. So that backbone that I showed you is actually a log of events that are happening within your application, and it's immutable. So that data, those records aren't going to be deleted or anything. Essentially what happens is if a state changes within your application, it essentially would produce a new event that would be appended onto the end of that topic. So it is immutable, they won't be deleted. So it can act as a log essentially of all of the events that have happened in your system. And what you can do is periodically throughout your application, you can actually take snapshots of that log, and you can store them in persistent databases, for example, if that's what you'd like to do. Just in case Kafka goes down or something, you can do that, and that enables you to have sort of a more permanent store of that event at that time. Hopefully that answers that question. Reactive only makes code better when your app is small. Do you agree or disagree? Oh, good question. I would say I would disagree with that statement. If you take a look, if you head to the Lightbend website, they have some really fantastic user stories where they go through different companies that are clients of theirs and their applications. Huge applications like Walmart, for example, and Verizon, who have very large user. We're in the thousands, if not millions, of users for these websites, and they are huge applications, and they are making fantastic use of Reactive. So I would say it's definitely not the case that you have to have a small application. I think Reactive can be beneficial, or at least the principles of Reactive, the behaviors I mentioned, can be useful for any application. Everyone can benefit from it. And if you check out those user examples, those user stories, those client stories, it'll give you an idea of the different types of applications that are utilizing this technology. So head over to the Lightbend website for that. Hopefully that helps. In light of your experiences, which framework provided for greater productivity and which one was more efficient and effective? Interesting question. I've actually written a blog post looking at, for example, different frameworks offer different advantages and different sort of ways of doing some of the reactive behaviors. So for example, a big difference in many of the frameworks is back pressure. So the way back pressure is achieved in, say, Vert.x is very different to the way back pressure is achieved in MicroProfile Reactive messaging or Akka, etc. So it can be really interesting to compare and contrast them. And I have written a blog post. If you head over to IBM Developer and go to the Reactive Systems section, you'll see I've authored several articles on there, and you can check out the one where I've gone into sort of the differences between some of the reactive frameworks, especially in regards to back pressure. I would say I've mostly used Reactive. I've used a little bit of Akka, I've used a little bit of Vert.x, and I've used quite a lot of MicroProfile Reactive messaging. They offer different things depending on what you need. So I would say it's completely down to your application, because if you're already using Akka, it might be really useful to use something like the Alpakka and the Akka framework. But if you're using microservices, it can take quite a lot to convert to an Akka-based framework. So you might be more interested in Vert.x or MicroProfile Reactive messaging. So I would say it's really down to each specific application. I'm gonna take the consultancy answer here and say it depends. But yeah, if you head to that page, that IBM developer site, you can check out some of my articles there where I go through some of the frameworks. Can Reactive Kafka have lags? How do you resolve lags there? Reactive Kafka have lags. So I guess, for example, if your application goes down, so let's say Kafka goes down, for example, this is where back pressure comes in, because essentially you're going to have to wait until Kafka comes back up to be able to send messages. So I guess, yes, in that case, there can be a lag. But once Kafka comes back up, Kafka itself acts as a buffer a bit. So Kafka itself can store messages and logs. And if your consumer goes down, for example, and it comes back up again, it can go back to the offset it was at and essentially catch up. So there might be a slight lag in terms of it spending time to catch up with the records that it's missed whilst it was down. But generally, it can just go back again and start reading, and it will eventually catch up. So there can be a slight lag. It just depends on how you architect your application. Because if, for example, you would rather there be no lag, but you don't mind missing records, you could specify to your application to not start at the offset it committed, but to instead skip them and start at the latest message. So it really depends on how you architect your application and what's important to you. There can be lags, but they're usually resolved because of the back pressure implemented and the natural buffer that Kafka provides. Hopefully that answers all those questions.